This is lecture it's lecture 10 for this course on Introduction to Differential Geometry. And in the previous lecture, we had started with normal and geodesic curvatures. And we learned that the shape of a surface is very much influenced by the curvature of surface of curves which lie on the surface. And a measure of to understand how much a surface curves can also be determined with by using the curvature of the curves which populate the surface. So here we have just in the schematic here, I have tried to show we have a tangent plane here corresponding to at some point, and then at some point P, if that's how it is. And we have the surface here denoted by S, a portion of the surface. And we have this curve parameter expressed as gamma, denoted as gamma, whose tangent gamma dot is, of course, lies in the tangent plane at that point. And it's the double derivative of gamma, which is also the acceleration, so to speak, of the curve, is perpendicular to gamma, right? And at this point, the normal to the surface is n vector. And it so happens that n vector and gamma dot are perpendicular, and their cross product is n cross gamma dot. It will be, of course, perpendicular to the plane dominant plane spanned by n vector and gamma dot vector. So this gamma double dot is also perpendicular to gamma dot. And this is what we have shown here. Right? So which makes that gamma double dot exists or resides in n vector in the plane spanned by n vector and n cross gamma dot vector, right? So this is where we have expressed gamma dot as a linear combination of n these two vectors, and the components are given by kappa m and kappa g. And then we had talked about a definition which goes as the scalars kappa n and kappa g are called the normal curvature and the geodesic curvature of gamma, respectively. Right, so now both kappa n and kappa g change sign when n vector is replaced by minus n vector, which is very obvious from here. So on a general surface, only the magnitudes of kappa n and kappa s, kappa g are well defined, right? Okay, so then now we let's define a proposition here. So here we can say that kappa n is just the component of gamma double dot along n vector, right? And likewise, the geodesic curvature kappa g is the component of gamma dot along n cross gamma dot vector. And of course, the principal curvature of the curve is kappa square, and it is just the magnitude of, or the sum of squares of kappa n and kappa g. Now, based on this schematic here, what we have is that kappa n is equal to kappa into kappa n. Kappa n is equal to kappa into cosine theta, or cosine phi, as we can see from the figure here. Right, so what we can say that is kappa n is equal to kappa into cosine phi, and kappa g is equal to plus minus sine phi, kappa sine phi. Right, and so this here follows from, since we know that gamma double dot is equal to uh, kappa n and kappa n and some normal vector to the curve, right? So when we take the dot product with respect to n vector. So say gamma double dot n is equal to, sorry, this will be kappa n because this is the principal curvature, right? So gamma double dot n is equal to k n dot n. And mind you that n is also along the same direction as gamma double dot. So this means that this is equal to k cosine phi, since phi is the angle between them. So therefore, and this is equal to kappa n, right? And then kappa g follows from square root of course, plus minus of k square minus kn squared. And this gives us plus minus k into sine phi. This is how we have got the expressions, right? Okay, so moving forward, let's list another proposition. So it states that if gamma vector is a unit speed curve on an oriented surface, as its normal curvature is given by kappa n is equal to the bilinear symmetric bilinear form defined for the second fundamental form. And in this case, if sigma is a surface patch of the surface of S, and the curve lying on the surface is equal to sigma as a function of two parameters, which are themselves functions of t, right? So, and this is a curve in sigma. Then kappa n is equal to L u dot squared plus 2m u dot v dot plus n v dot squared. So this is how we define uh, the curvature, I mean the normal curvature of the curve lying on the surface, lying in the surface, right? Okay. So the proof of this goes as, so since gamma vector is a tangent vector to S, then because of which n vector dot gamma dot vector is equal to 0, isn't it? So this means that n vector dot gamma double dot is equal to minus of n dot gamma dot, right? So we have kn is equal to n vector dot gamma double dot is equal to minus n vector dot gamma vector, and this can be uh, said to be this bilinear product, right, of the Weingarten map W as a function of gamma dot and gamma dot. And this we learn is the same as gamma dot, gamma dot, right? So now since, and this follows from the fact that n vector dot is equal to the derivative of the Gauss map, which is equal to minus of W of gamma dot. Right. So if for revision purpose, let's get back to how do we define this Weingarten map. It is just minus derivative of the Gauss map, right, at a point P. And it so happens that the second fundamental form is the bilinear form, which is given as V comma W, which are vectors in the both of which are vectors in the tangent plane at point P. Then this is equal to the bilinear form of Weingarten map, comma W vector, right? So, right. So this is how we had defined for the bilinear form for the second fundamental form in terms of V and W. And we had also followed through a lemma where we showed that it is actually true, right? So, and here it should have been minus, right? Okay, so, and then we could define LMN and also shown that W minus NU dot sigma vector U is equal to L of, which is also the bilinear form defined on sigma U and sigma U vectors, right? And we also learned that the Weingarten map is self-adjoint, and I also stated the condition for the self-adjoincy of any operator, right? Okay, so coming back, uh, so we'll have a corollary here. So it states that the curvature kappa, the normal curvature kappa n, and geodesic curvature kg of a normal section for normal section of a surface are related as kappa n is equal to plus minus kappa and kappa g is equal to 0. Now, what is a normal section? So that's the first thing that comes in mind. What is a normal section? So normal section of a surface is a curve gamma vector which is formed by the intersection of the surface with a plane uh, plane some pi that is perpendicular to the tangent plane, so to speak, say TPS of the surface at every point of gamma vector. So this is what so in that case, at every point of gamma vector, we always have a plane which is perpendicular to every point of the curve, right? And it is perpendicular to the local tangent plane at every point of the curve. So this clearly implies that if we look at the schematic here, in such a scenario, what would happen is that gamma double dot will be pointing in the same direction as n vector, right? Because in that sense, all the planes uh, will be perpendicular, like the plane pi will be perpendicular uh, to every point along the curve, and in such a manner that the so schematically that's how it would be. So we have this tangent plane, and this is our pi plane. It will pass here. Or maybe just keep it. And this is TPS. Then in that case, right? So this what the intersection happens at. So this is the intersection gamma, the portion of gamma, infinitesimal at, right? Some infinitesimal portion of the gamma. So so the tangent to TPS is of course the normal is given by n vector, and the n vector lies in such a plane at every point in the curve. So that's what it is, right? So in that case, gamma double dot is parallel to n vector. So because of which we won't have any component along n cross gamma dot vector. And that's what we call such curves for which this happens is called a normal section to a curve, right? Okay. So now let's move on to discussing about parallel transport and covariant derivative. Covariant derivative. Okay. So let's formally try to build an intuition about parallel transport, right? So suppose we are someone is riding along the equator, riding on a vehicle with on along a path which is coinciding with the equator, right? So as the person is driving forward, he is his perception of velocity, he to him the velocity is constant, right? For the person riding on the car. However, for an observer who is who is say looking at the person riding on the along the equator, to this person it will seem that to this person, of course, velocity keeps on changing because the direction of velocity keeps on changing, right? So, and since velocity is a vector, so the change in direction, even if the magnitude is constant, still is considered that the velocity happens to be changing. right? So there are 2 points here, 2 observations. First one is that to the rider, uh, the velocity is constant. Of course, if velocity is constant, then of course speed also is already constant for him. Of course, constant, right? However, to an observer, in space, the velocity keeps on changing. The rider, so this is equator, and I must make it clear, is changing, right? So this is what we see here. So the issue is that for a rider who is traveling along the equator, to him or her, the uh, the tan the person is only able to see the tangential component of his motion, or tangential component of the acceleration, which, so to speak, which that's how it seems to him, right? But however, for the observer, the acceleration at any point, even if the person is traveling at a constant velocity, a constant speed, even then there is an acceleration which, because of, by virtue of the circular motion, this motion has an acceleration which always points towards the center of the earth. And to the observer outside the space, there is no tangential component of the acceleration. It always is radial, right? So there is this paradox which goes on, right? So now let's try to understand it from a different, from a differential geometric point of view, right? So given that, say, we have gamma vector is a curve on a surface S, and let V vector be a tangent vector field along gamma vector, which is to say that uh, a smooth map from an open interval alpha beta to R cubed, such that V vector, of course, as a function of t, is an element of the local tangential vector, local tangent planes for all t. For all t is an element of alpha, gamma, beta. Right? So to the observer, in this case, rider, right? So to the observer, the rider who is moving along the curve gamma vector, the perceived rate of change of V vector is the tangential component of gamma vector of V vector dot. So which means that is the orthogonal projection of V vector is equal to dv vector by dt, right? And that too on the tangent plane, the local tangent plane, right? Now, if n vector is a unit normal to sigma vector, then what happens is the component of uh, n v vector, which is perpendicular to the surface, is v dot n and n vector, right? So of course the tangential component is just from the vector rule of addition. The tangential component of v vector is given as grad gamma vector, which is the rate of change of v vector along gamma vector, is equal to v vector minus v vector dot n vector. And what we see is in this case that even if, and this is invariant even if invariant to the change in sign of n. So even if n is negative, it doesn't matter because we have two n's uh, in this expression. So the negative will just cancel out, right? So which means this implies that uh, gamma vector grad of with respect to gamma of v vector is well defined on any surface, even if it's orientable or not, right? Is defined on any surface. So the schematic goes as, let me try to draw here. So we have the tangent plane, and this will be at some point, right? So, and we'll have the curve right? And now let's define a curve on this. So say this gamma, and of course this is the curve. Right? So locally, say the tangent vector field along v vector will be, say, along certain directions. So say this, this, and this here. Right? And so these are just the component, the direction of v, which is the local tangent vector to this curve gamma. Fine. And at this point, say we have a normal, which is given by, say this is the normal to the surface. Right, so V is in this direction. So at this point, say where the normal is located, you will have V vector, which is going to be perpendicular to V, of course, and say it is pointing in some direction, right, in this fashion. And this is our V vector dot. So the locally, the component of V vector, which is tangential to the surface, is this, right? And that's what we have expressed as gamma grad of gamma vector V vector, right? So this is the that we are talking about. So this is the one. So yes, just use a different color. Okay. So this is the direction about, right? Okay. So now we define a proposition here. So let we have a definition here. So let gamma vector be a curve on a surface, and let V vector be a tangent vector field along gamma vector. Fine. So we have a gamma vector on us and V with a tangent vector field along gamma vector. Then the covariant derivative of V vector along gamma vector is the orthogonal projection grad of gamma vector V vector of dV vector by dt onto the tangent plane T gamma vector T of S at a point gamma vector T. Okay, so that's what, so now we understand what we call as the covariant derivative, right? So covariant derivative of gamma is the orthogonal projection grad V of V dot along the tangent plane at a point gamma dot. Now it seems that here, so we have an observation here that an inhabitant, in this case the rider of the surface S, would perceive V vector as being constant along gamma vector if gamma vector grad of gamma vector grad of V vector with respect to gamma is equal to 0. And so in this case we also call that, so in this case V vector is sometimes said to be covariant constant, right? This follows up with a definition, with a proposition. Now, it states that a tangent vector field V vector is parallel along a curve gamma vector on a surface S if and only if and only if V vector dot is perpendicular to the tangent plane. Of S. At all points of gamma vector. So what we see even in the schematic that V vector is nowhere parallel to gamma vector, right? So in this case, what happens is that gamma vector is pointing this way, but we always see that they are not, they do not point in the same direction at any point of gamma vector in general, right? So, but if you would want to have a vector field which is always parallel to the curve on a surface, this would only happen if V dot vector is perpendicular to the tangent plane at all points of gamma. In that case, what would happen is that V dot is, uh, of course, points out to the principal curvature of the curve, right? And if the principal curvature, yeah, so it's like the principal direction, if you can say that. So, or the normal vector, sorry. So the principal normal vector to the curve, if it happens to be parallel to the unit normal to the surface, in that case, we would have V vector to be parallel along the curve gamma at every point, right? So that's what it implies here, the proposition here, right? So in that case, what happens is that grad of V gamma vector, V along gamma vector is equal to V minus V dot minus V dot n and n vector. Now it so happens that if V vector is parallel, so parallel implies that some multiple, say maybe mu n vector, right? Then this implies that V dot n vector of n vector is equal to, it's just to say that mu into n dot n is mu in n vector. So it's the same as V dot vector. So this implies that grad of gamma vector along V vector is equal to 0 vector, right? So this is what happens in such scenarios. Now let's move on to an interesting proposition here, which is very useful to us. So we want to establish the existence of parallel tangent fields, and we would want to express the covariant derivative in terms of the parameters uv of a parameterization sigma on the surface. So at first, this proposition is also famously known as so it's also famously called as the Gauss equations. So the proposition Gauss equations. So it states that let sigma vector u comma v and let it be a surface patch with first and second fundamental forms as and second as E du squared plus 2f du dv plus g dv squared and L du squared plus 2m du dv plus n dv squared, right? So these are the two fundamental forms. Now then, you can express sigma vector uu is equal to gamma 1 1 1 sigma u vector plus gamma 1 2 2 sigma v vector plus L of n vector, right? The and then we have sigma uv is equal to gamma 1 to 1 sigma u plus sigma 2 1 gamma 1 to sigma v this would be 2 plus m and n vector, and finally we have sigma vv is equal to gamma, this would be 2 here, sorry 1 here, and this would be 2 to 1 sigma u plus sigma 2 to 2 sigma v plus n into n vector, where sigma 1 1 1 sigma 1 1 2 or essentially we have I alpha beta and some say delta here. And alpha beta gamma is equal to 1 2, that so these are called as Christoffel symbols. Christoffel symbols, right? And so what is the physical explanation for such Christoffel symbol? What do they actually represent, right? That is the question that comes in mind for. So fundamentally, what we say here is that Christoffel symbols, they actually tell us. So I'll just write it down here. So gamma, delta, alpha, beta gives us the measure of variation of the, or the maybe the measure of the derivative of basis vectors along, or maybe we can say the representation of the directional derivative, because that's what we imply here. along along basis vector along basis vectors. I'm sure there's too much of a word salad here going on. So let's try to decode what we are trying to say here. So maybe we can just say that partial derivatives of basis vectors with respect to the parameters in the basis vector in the basis. That's what we can say. So let's try to decode this. So essentially, what gamma, alpha, beta, delta does is it tells us about so the variation of sigma, say maybe sigma u, right, with respect to I should just say it sigma alpha and and alpha and some sort of a say maybe x beta, and let me just tell you that x1 is equal to u and x2 is equal to v for surfaces, and we know that alpha beta gamma varies from 1 to 2. This dotted with sigma delta. So what does it tell us? It tells us the component, right? So it tells us the component of the partial derivative of these basis vectors with respect to the parameters in the basis, in the same basis. So that's how we essentially write it down. And we say that sigma 1, 1, 1 is equal to, so in this case, sigma alpha is equal to 1, essentially implies that we are talking about sigma u, and x1 is u dot sig delta 1 is 1. So this is what we are talking. This delta 1 is also is equal to u. So that's how we define Christoffel symbols. So of course, I'm not going to derive here in detail, because from this expression, it is not very difficult to derive it. So what we will do here is I'll just give the expression in terms of the uh, first and second fundamental forms. Sorry, in terms of the first fundamental form. So EU minus 2FFU plus FEV divided by 2 into EG minus F squared, comma, this 211 is equal to 2EFU minus EEV plus minus FEU divided by 2E F minus divided by, of course, 2 EG minus F squared. Likewise, sigma 1, 2, 1 is equal to GeV minus FGU divided by 2 into EG minus F squared, comma, sigma 1, 2, 2 is equal to EGU minus FEV divided by 2 EG minus F squared, and sigma 2 to 1 is equal to 2 GFV and GGU minus FGV divided by 2 into EG minus F squared. Right, comma, sigma 2 to 2 is equal to EGV minus 2FFV plus FGU divided by 2EG minus F squared. So that's what it is, right? And this can be obtained quite easily, so to speak, uh, when knowing the fact that the basis that we can define sigma u, sigma v, and n to be the local or the basis for R3, right? And then we can just expand along all these lines in order to be able to obtain this. Right. So let's have some more proposition here. So essentially, I'll just give a hint. So how to derive it first. So sigma u, sigma v, and n vector is a basis of R3, and the scalar and scalar functions alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3 are the components or the scalar functions satisfy, right? So what we have is sigma uu is equal to alpha 1 of sigma u plus b alpha 2 sigma v plus alpha 3 n vector. Likewise, sigma uv is equal to alpha is equal to beta 1 sigma u plus beta 2 sigma v plus beta 3 n vector, right? And likewise, we have sigma vv is equal to gamma 1 sigma u plus gamma 2 sigma v plus gamma 3 and vector, right? And using this, we can derive the expressions, whatever is necessary, right? Okay, so now we move on to a definition here, which just talks about the parallel transport, right? And I'll just be stating it. So states that if P vector and Q vector are 2 points in a curve gamma vector on a surface S, the covariant derivative enables us to associate to any vector in the tangent plane TPS a vector in the tangent plane TQS, right? Now, indeed, what happened is, say P vector and Q vector and correspond to or be such that gamma vector at T naught is equal to P vector and gamma vector at T1 is equal to Q vector. Now let V naught vector be an element of TPS. So V naught vector is just some starting point of origin point of the gamma vector, right? So then and let V vector T be the unique parallel vector field along gamma vector such that V naught at T naught, V vector at T naught is equal to V naught, right? And let V vector at T1 is equal to V1, right? And both of them be contained in TQS, right? Now the definition states that, in fact, furthering along that there is a map which is called gamma, PQ, and small gamma, right? So pi, PQ, and gamma, which maps from TPS to TQS, that takes V naught vector is an element of TPS to V1 vector is an element of TQS is called, so this map is called parallel transport. From P to Q along gamma vector, right? So with this, we have a proposition and proposition. So we have 2 points to this proposition here, that pi PQ gamma from TPS to TQS is a linear map. And just to add, parallel transport has a very wide applicability in parallel in computer graphics, right? Or in discrete differential geometry, that forms the basis for such computer graphics. So pi PQ gamma is an isometry. That is, it preserves lengths and angles. Right? So with this, we finish the first fundamental, the second fundamental form part. Now we'll start with the Gaussian and mean and principal curvatures, right? So we'll start with this topic today. So we have Gaussian, mean, and principal curvatures. So this is the topic. Okay. Yeah. So the idea is we want to extract certain geometric information from the second fundamental form of a surface. Or of course, it also has to do with the Weingarten map. So we'll start with the what we call as the Gaussian and mean curvatures. We want to first define what they mean. So Gaussian and mean curvatures. Right. So it's accompanied by a definition. So it says that let W be a Weingarten map of an oriented surface S at a point P vector is an element of S, right? The Gaussian curvature K and mean curvature H of S at P vector are defined by K is the Gaussian curvature. It is defined as the determinant of the Weingarten map, and H is half of the trace of W. And understand that the determinant happens of a linear map, right? So note that the determinant and trace of a linear map, such as Weingarten map, it is actually the determinant and the sum of the diagonal entries of a matrix of the linear map with respect to any basis. So first we have to represent this Weingarten map in terms of some basis, and then we will, so ideally, maybe schematically, that's how it is. So we have this Weingarten map. It is a tensor. So we first represent in any basis. So then we would get an array of a matrix of numbers. Of course, W will have it will have 2 cross 2 matrix, right? So first, second, third, fourth, four elements will have in this. Then now we have a matrix. So K, so we'll just call it, say, so this we can call it matrix form of W, right? So the K will be equal to determinant of matrix form of W, and H is equal to half of sum of diagonal elements of the matrix representation of W. So this is what the mean and curvatures are. And it is to be to recall that uh, if the sign of the normal vector changes, then what happens is it also changes, right? So since we knew that W along some direction says sigma u, it was we determined as minus n vector u. Right? Likewise, W of sigma v is equal to minus of nv. Right? So we can always form a linear combination of any expression in terms of sigma u and sigma v, any vector lying in the tangent plane. So that will also appear as the linear combination of minus nu and minus nv. Now, if n vector changes its sign, then even W changes sign. And this is, of course, this goes hand in hand, right? We cannot separate one from the other in this case. So this is what we have been right. So this is one thing. And if so, what happens even if this change K is a product of in a sense that K is the determinant, right? So it is not, it's invariant with respect to sign change. So K is invariant to sign change of n, but H is dependent to sign of change of n vector. And that's the reason we always say that uh, Gaussian curvature is also something called as the intrinsic curvature. So something which does not depend on the choice of representation, right? However, H, the trace actually depends on the choice of representation, right? So because of which it so happens like that. Okay. So in a sense that K is defined for any surface. For any surface S, right? So be it orientable or not. Now, and H is defined up to, is well defined up to a sign change, up to a sign in that sense. Okay. So now our immediate goal is to understand or to derive the expression for the right. We want to derive the expression for the Gaussian curvature and the mean curvature. So it's like a derivation of H expressions, right? Of explicit expressions of K and H. Right, so that's what we're going to do now. So at the outset, let's sigma UV be a surface patch with first and second fundamental forms E du squared plus 2f du dv plus g dv squared, and then you have L du squared plus and 2m du dv plus n dv squared, right? So these are the first and second fundamental forms. Now we define we define this respectively, of course. So we define symmetric 2 cross 2 matrices with F1 and F2 by, they will be just populated with these coefficients. So F1 is equal to E F Fg, and F2 is equal to Lm Mn. Right, so this is what it is. Now we note down a proposition. So the proposition states that let sigma vector be a surface patch of an oriented surface. S, right? Then with the matrix of W, the Weingarten map at point P on surface S with respect to the basis sigma u comma sigma v of TPS is F1 inverse into F2. So that's what it is, right? Now let's try to understand it, and let's derive whatever is necessary for this. So say that as we learned that Weingarten map when applied along the first basis vector of this surface at any point, this is equal to minus of nu, and W of sigma v is equal to minus of nv, right? So what happens is we can represent nu, since nu is going to perpendicular to n, so which means it has to lie in sigma u and in this in the tangent plane, right? So sigma u and sigma v. Likewise, nv will also lie in sigma u and can be represented in this form. So this implies that the matrix representation of W is given as, so we can write this down in the following manner: minus nu vector and minus nv vector. This is equal to sigma u and sigma v, right? And then we have a, b. So that's how we obtain nu, right? Nu is equal to a sigma u plus b sigma v. Likewise, minus nv is equal to c sigma u, c sigma u plus d sigma v, right? So this is the matrix representation of W. So this is matrix representation of W, the matrix form of W. Right? Now what we can do here is, let's this one be a star and let it be double star. So multiply star by sigma u. Then this gives us minus nu dot sigma u is equal to, what it should be, take dot product, right? Dot product with, this is equal to a sigma u dot sigma u plus b sigma u dot sigma v. So this gives us, this implies that minus nu dot sigma u was what we call as L. Then we have a into sigma u is b plus b sigma u dot sigma v is f, right? Likewise, with dot product of this one with sigma u, sigma v. So then we have minus nu dot sigma v is equal to a sigma u dot sigma v plus b sigma v dot v. So this implies that minus nu dot sigma v was m, and here we have u dot sigma v is f, and v dot v is g, right? Okay, so now dot product of with sigma u is minus n v dot sigma u is equal to c sigma u dot sigma u plus d sigma u dot sigma v. And this implies that there's again a this is the expression for m, and then on this we have sigma u dot sigma u is just e, and d sigma u is this f. Likewise, double star with sigma v is minus nv dot sigma v is equal to c. And then we have this as m, and this as f, and d g. Right. So essentially, what we have been able to do is that we have been able to obtain the relations between the coefficients of the first and second fundamental form, and also been able to connect it to the matrix representation of the Weingarten map W, right? So what we'll have here is that um, so what we'll have is that combining all these equations, 1, 2, 3, and 4. So assembling like 1, 2, 3, and 4 in into a matrix equation, into a matrix equation. Then what we're able to do is we have L here, and let's build it up. So L is equal to E into A and F into B, right? L is equal to E into A plus F into B. So we'll have B here. Likewise, M is equal to E into so let's do this. M is equal to right. So M is equal to, let's do it here itself. Sorry, M is equal to E into C plus D into F, right? Likewise, here M also has another expression. M is equal to uh, A into F, A into F plus G into B. So this will be G here. And finally, N is equal to C into F. So this goes C into F plus D into G. Right? So that's how we have been able to assess. And this implies that this is the second fundamental form, representation of second. Then this is the first fundamental form. And this is our matrix corresponding to Weingarten map A, B, C, D. So therefore, A, B, this Weingarten map representation A, B, C, D. And this will be equal to, you can call it F inverse, because this will be inverse into F. So that's how we do it, right? Okay. So essentially, we have been able to determine all this, and we can also try to form an explicit form of by. So F inverse is uh, 1 minus EG minus F squared, and then we have to find the adjoint, right? So adjoint is E is G, adjoint of element E is G, F is uh, 1 plus, so minus F, right? And again, F is minus F, and then G is E. Right? So this is our inverse of F, and then we have L, M, M, N. Right? So this is what we have. And this is equal to 1 by EG minus F squared. And then we have GL minus FM. And GM minus FN. And we have MEM minus FL. But maybe just to simplify, better to have second fundamental form in the first sum, right? So we can have LG minus MF, then MG minus NF. Then we have ME minus LF. And likewise, NE minus MF. Right? So this we have been able to get the expression for ABCD. Sorry, ABCD. Okay. So from here we can easily determine uh, like as we recall, therefore Gauss curvature K so Gauss curvature of K is equal to a determinant of F inverse. Of course, that's what it was, F inverse. First of all, it was determinant of the matrix I want to W. This is equal to determinant of F1 inverse and F2. And this, recall from the property of this is different determinant of F1 inverse into determinant of F2. And this is equal to clearly the determinant of F2 divided by determinant of F. And then the determinant of is very clear, Ln minus M squared by EL EG minus F squared. Right? So therefore, K is the Gaussian curvature is Ln minus M squared divided by EG minus F squared. Fine. Okay. Now how about mean curvature? Mean curvature H is the half of trace of the matrix representation W. Now half of trace is this is equal to half, and of course half into 1 by EG minus F squared and LG minus MF plus NE minus MF. So this implies that rather we should just have this, and then H is equal to LG minus 2 MF plus NE divided by 2 into EG minus F squared. Right? So and likewise for H we have, right? So we can do a few examples. So examples. So let's start with an example. So we consider the surface revolution again. As sigma uv is equal to f of u cosine v f of u sine v comma g of u, right? And we assume that where f of u has to be greater than 0, so because of the fact that we would not want the body to penetrate into itself, and then we have f dot squared plus is equal to 1, and this is everywhere. So implying that the profile plane or the profile curve happens to be uh, a unit speed curve, right? Okay, so now let's move on to solving this. So you have sigma u is equal to, and our goal is determine A and H. Now sigma u is equal to f dot. So dot indicates, so d by du is indicated by dot, right? So f dot cosine v, f dot sine v, comma g dot, right? And then we have sigma v is equal to f dot, sorry, it's equal to minus f sine v and f cosine v, comma 0. So this is done. Now sigma uu is equal to uh, f double dot cosine v, f double dot sine v, and g double dot, right? And then sigma uv is equal to minus f dot sine v, comma f dot cosine v, comma 0, right? And then finally we have sigma vv. So this is given as minus f cosine v minus f sine v 0, right? So we have this. Now we can clearly construct the metric coefficients or the coefficients for the first and second fundamental form. So E is equal to sigma u dot sigma u, which comes out to be f dot square cosine square v plus f dot square sine square v plus g dot, right? So cosine square sine square gets consumed, I mean gets uh, compact, I mean the form, I mean it's just one, right? So then we have f dot squared d dot squared. So we have f dot squared plus z dot square, and this equals 1 from the condition of unit speed curve. And then we have f is equal to sigma u dot sigma v, and this comes out to be 0 because they are identically cancelled. And then we have g is equal to let's trace this and then and write everything on one page. This as well. Okay. Now g is equal to sigma v dot sigma v, and this comes out to be f squared. Likewise, now we have to determine n vector, and n vector is equal to sigma u cross sigma v divided by norm of u cross sigma v, and then sigma u of sigma v is equal to the first term will have minus f g dot cosine v. This is the first term, and second term is minus f g dot sine v plus 0, right? And the third option is f dot cosine square v, f dot f cosine square v minus plus f dot, so it is like f dot, and this divided by the square root of this is f g dot whole squared plus f dot whole square, and this comes out to be f square comes out of the square root, so we'll have just minus z dot cosine v and z dot sine v f dot. So this is our n, right? So now L is equal to sigma uu dot n vector, and sigma uu dot n vector happens to be this also minus here. Sigma uu dot n happens to be f minus f double dot g dot cosine square v, and then minus f double dot g dot sine square v. So we have double dot g dot z, and then we have plus f double dot f dot g double dot, right? And then n is equal to sigma uv dot n, and this comes out to be f minus f dot into minus z dot is plus f dot z dot and cosine sine. Then we have minus, so this is identically 0. And finally, we have n is equal to sigma vv dot n, and this comes out to be so we'll have plus fg dot cosine square v plus fg dot sine square v. Yeah. So we have just fg dot. Okay, so now let's use the expressions to determine. Therefore, the Gaussian curvature is Ln minus m squared divided by Eg minus f squared, and L into n is like f dot g double dot minus f double dot g dot into n, which is f g dot, and minus m, so m is 0, so no issue, and divided by 1 into f squared minus uh, f squared is 0, so it's like 1 into f squared. So this eventually comes out to be so all we have is f dot g dot minus f double dot g dot into fg dot divided by f squared. Right? So we can try to simplify this further. So the goal is like, say g f cancels out, so we can have f dot g double dot minus f dot g dot squared, right, divided by f. Right? So this is, and from our expression that f dot square plus g dot square is equal to 1, we can have f dot f double dot. This implies that f 2f double dot plus 2 g double dot is equal to 0. So therefore, g dot g double dot is equal to minus of uh, f dot f double dot. Right? So this comes out to be, using this here, so we'll have f dot minus f dot f double dot and then minus of f double dot g dot square divided by f, and this easily comes out to be minus f dot squared f double dot minus f double dot g dot squared divided by f. And so we can take minus f double dot as common factor, and then we have f dot square plus z dot square divided by f, and it can clearly see that f dot square plus z dot square is equal to 1. So therefore, k is equal to minus f double dot by f. So these are Gaussian curvature. And as with regard to the mean surface h, mean curvature h is equal to, we have a nice expression here, and it goes as Lg minus 2mf plus n e divided by 2 into Eg minus f squared, right? Let's plug in the values here. So Lg is f squared and then f dot g double dot minus f double dot g dot, right, minus 2mf. So both these are zeros, plus ne. Ne is just plus f g dot divided by 2 into Eg is just 2f squared. You can try to expand it here as well, this as well. So all we'll have is, do we see anything happening here? Except for the fact that f one of the terms gets cancelled out. So we'll have f into f dot g double dot minus f dot double dot g dot plus g dot divided by 2f. Apart from this, we can't see anything which can be cancelled out, right? So yeah, so there's our mean curvature. Let's do one more example for now for a corresponding to a ruled surface. Now for a ruled surface, we have the surface patch as sigma uv is equal to gamma vector u plus v into delta vector u, right? Now, sigma u vector is equal to sigma, this one is just gamma dot plus v into delta dot, right? And sigma v is equal to just delta sigma uu is equal to gamma double dot plus v delta double dot, right? And then sigma uv is equal to uv is equal to delta dot, right? And then sigma vv is equal to of course 0. Then we construct the normal vector, which is sigma u cross sigma v divided by the norm of sigma u cross sigma v, and this gives us sigma u cross sigma v is so what we have here is that it's of course not going to be a it's just there is nothing much to simplify here. Gamma dot cross delta, until we know the explicit expression, we can't do much. So let it be as if like this, right? Now what we have is, so let's determine the coefficients. So E is equal to sigma u dot sigma u, and this comes out to be just gamma dot plus v delta dot into gamma dot plus v delta dot. Okay? And we don't know whether delta dot is parallel or so. Let's keep it as it is for general case. And g is equal to sigma u dot sigma v, and this also comes out to be some expression. And f, of course, this one was f actually, and g is equal to sigma v dot sigma v. So this comes out to be del of vector whole square, norm of this quadrant. And L is equal to sigma uu dot n vector, and this comes out to be um, so this comes out to be into n vector, right? So we will have gamma double dot n plus v delta double dot n dot n. M is equal to sigma uv is equal to delta right? So this is what's happening here. The so n will be equal to likewise. So n is going to be just 0, right? So therefore, the mean the Gaussian curvature is ln minus m squared divided by eg minus f squared, right? And so at best what we can do here is that we will have L into m is 0, L into n is 0, so we have minus delta dot n whole square divided by Eg minus f squared. And let's try to expand this. How will Eg minus f squared look? So delta dot. So Eg is gamma dot norm squared plus 2v delta dot into 2v gamma dot delta dot plus v square delta dot norm squared, and this multiplies with g, so we'll have right and minus f, so gamma dot plus v delta dot delta dot. So we see that we cannot make much out of this, right? Like we not, provided we have certain conditions on say delta u itself. Say if delta u is a unit vector. Say if delta u is a unit vector, then what we can have is that Eg minus f squared is equal to so we'll have so this will come out to be 0, and this is going to be 1, right? And even if say even if gamma is also unit vector, a unit split curve, gamma vector is a unit split curve, then what happens is even this will be 1 plus 2v gamma dot delta dot plus v squared, then delta dot whole squared minus gamma dot delta dot plus v plus 0, right? So is this going to be greater than 1? Greater than 0? Let's see. So this is of course always greater than 1, greater than 0, this. So yeah. So I think I'll just close today's session because we have been able to, of course, did talk about Gaussian curvatures and all. And in the Gaussian curvature and mean curvature, in the next session, we will try to finish some of the other important topics that have been discussed in our, and of course we would be trying to make it faster because there are few topics in mechanics that I would like to discuss. So what we'll do is we'll talk about principal curvatures and discuss a bit about Gauss theorem egregium, and we would eventually start with dealing little bit on Ruds and if possible on ripples. So yeah, with this I'll close today's session. Yeah.